Okay, so use this to check your work and make sure you did things correctly. Check the wheel if your amino acids are wrong and confirm that, yeah, you probably put the tRNA in instead of the mRNA. Go through a couple of the mRNA, make sure you can do it. But that is by far the most common mistake. Try not to make that mistake again, though. Like, I do this, but then some of you still do it on the test. Like mRNA, not tRNA. You can make a wheel that'll work for tRNA. But this one isn't that, because we want you to be able to cheat, right? We want you to be able to not go all the way to tRNA. If you can, just go to DNA, mRNA, and then there you go.
Where it says mRNA only, we not use that. I don't know.
You go ahead. You're not going to be using that. I'll print that wheel on the test.
See how.
My dad does the same. It's small spiders. Like you're that's uncanny.
That is boring. I mean, I did ask this when I had this decoration.
That's a good idea. I like that.
Oh, yeah, we were laughing at you. Oh.
Like Beavis. No, I guess that's Butthead. Butthead. Okay, so that is, I'm going to assume now that you know how to do this. Okay, because we are now moving into using what you know. Grab your notes. So we got to, right, we had done transcription. The mRNA came out of the nucleus. Ribosome clamped down on it. We drew that. The fact that the ribosome covers up 6 bases is no accident, because that allows one tRNA carrying its amino acid to float in and match up its anticodon with the codon. And the first codon usually is AUG with the anticodon UAC and the first amino acid methionine. One more clue that you're doing it right. I think all of those in your homework also started with methionine. So look for methionine and stop. It's not a guarantee that you're doing it right, but it's a pretty good sign. Still got 3 bases left in the ribosome, so the second tRNA floats in. Then you got to make a bond between the methionine and the leucine, and so the methionine gets stuck on the leucine peptide bond. Still got 3 bases to read here. So what needs to happen is this tRNA falls off. The strip of mRNA moves down 3 bases. New tRNA moves in. Chain gets stuck onto new amino acid. And the old tRNA falls off again. This doesn't stop here. In reality, this thing's way longer. And it keeps going and keeps going and keeps going and keeps going. Until, like you said, a stop codon. It keeps going until it hits either UGA, UAA, or UAG. Wait a minute. What happens if there's never a stop codon? Excellent question. You will find out today. Yeah, you could, because you could imagine a scenario where something happens and there's no stop codon, or something happens and there's accidentally a stop codon early. Those are 2 possible outcomes of a mutation, and we're going to talk about mutations today. So it keeps going till you hit stop. At that point, the chain gets cut loose. the chain of amino acids that's going to become a protein. It folds up into a functional protein. Sometimes it needs a little help from other proteins. Sometimes it just it's been folding since it started popping out, and everything else falls apart. Any questions about any of those steps that you discussed today? And how this all ends up? This is the hard part. Yeah, great. I think there are some proteins that don't start with it, but like the vast majority to where we say it's the start codon.
We were talking about like mutation.
Yes.
Like what kind of mutation would it be? Would it be like another eye or something like that?
So there's several possibilities with any mutation. I promise we'll talk about it. The ones that result in the kinds of things you think of as mutations aren't very common at all. But sure, yes, there are mutations that result in an extra of, say, a finger or another organ, right? Most of them are subtler than that. Okay, so protein structure-wise, when a protein folds up, here's a look at how it happens. It's a chain of amino acids. This is their representation of that chain before it's folded. And then there's different levels of folding. We call this primary structure. Primary structure is the order of amino acids. Secondary structure, where we get these kind of folds and coils. And then tertiary structure and quaternary structure is when we really start to see the shape of the protein, okay? That shape totally depends on which amino acids are there, right? The way it folds up by the end. This is hemoglobin, by the way. Hemoglobin, the stuff in your red blood cells that carries oxygen. It's just another protein coded for by DNA. And this one folds up in just such a way that it's really good at grabbing an atom of iron, the metal iron. That's in your blood, right? Well, it's in the middle of hemoglobin. That's the part of hemoglobin. The metal that protein actually grabs onto is what lets it stick to oxygen. If you have even one mistake in those amino acids, it's going to mess up hemoglobin, right? A mutation like sickle cell anemia. Sickle cell is one mistake in the DNA that codes for hemoglobin. What it does is make your red blood cells that are normally nice and donut shaped, makes them collapse into like a half moon shape and clog up your blood vessels. One mistake can do that. So let's talk about that. Let's talk about mutations. DNA mutations generally are caused by two things. Number one, something that can cause a DNA mutation is simply a mistake in replication. You remember replication, the copying of your DNA, copying of both strands. It was like your training wheels for learning what we just did. Kind of like transcription, but simpler. Now you have a whole system that you learned about in chapter 10 with mitosis. There's a whole proofreading system, right, that tries to guard against mistakes in DNA. That'll fix those mistakes, that'll keep the cell from reproducing if it has a mistake, and if all else fails, that'll make the cell basically self-destruct if it has a mistake. But sometimes mistakes get through. The other way mistakes can happen, due to no fault of your own, mistakes can happen from chemicals and radiation and other environmental factors that'll mess up DNA. We call those mutagens. Ultraviolet light is by far the most common. The kind of light that is shortwave enough to penetrate your cell membrane and your nuclear envelope and get in there and foul up your DNA. Most of the time, not a big deal. Most of the time, you just get a sunburn. Some cells die. It's fine. Every once in a while, you get that one kind of tweak in your DNA. It only takes one, right? It'll take a skin cell and basically remove its ability to stop dividing. Which is why most of the mutagens we pay attention to are the kind that can cause that one tweak, right? The kind that can cause cancer, which we call, more specifically, carcinogens. Those are most of the mutagens we worry about. Most of the mutations that we see in DNA are what we call point mutations, which are simply changes at one single point in the DNA. Either adding a base, subtracting a base, or replacing a base, essentially. Those are called point mutations. But it's worth differentiating the different kinds of point mutations, because some are definitely more serious than others. Substitution is one of the three kinds of mutations you're going to want to know. Substitution, for example, if we take this string of messenger RNA, or sorry, of DNA, and replace an A with a G. That is a substitution mutation. There was an A here, now there's a G. And tell me what the before and after amino acids are with this DNA. Again, this was an A, now it's a G. So what were the amino acids before the mutation? What are they now? That's what I want to know. Take a minute, figure it out on paper. This is always good practice. You're going to have to do this on a test. No, that's DNA. You can tell because, yeah, there's T's, right? So that is not, by the way, what you put into the decoder wheel. You've got a step to do before you use the wheel. You got to get from DNA to mRNA. Again, you don't have to go all the way to tRNA, right? But you got to do one. You got to transcribe that. You got to transcribe it from DNA to mRNA. What three amino acids were there before the mutation? Anyone? Riley, you want to give it a shot?
Before the mutation.
Before the mutation. Methionine, yeah, because that's how you know you're on the right track, right? That's usually the first one.
No. Leucine.
So it was methionine, leucine, because that's C, that would have been CUC, just leucine. And then, which is? Glycine. Good. Now that it's GGG in the middle, what is that second amino acid now? It's proline now. So leucine has become proline. Generally, that is the outcome of a substitution mutation. Either it changes one amino acid, or that last one, lysine. What if it was a mutation where what if this changed to a T? What would we get instead of lysine? Jane? You'd still get lysine. So sometimes mutations don't cause any change, right? Okay, so there's one thing. The other kind, which is actually two kinds, are insertion and deletion, where you add a base or you're missing a base. What does that say? Dog ate big ham. Now, a substitution mutation is the equivalent of saying, all right, well, let's take one of these and change it. Let's take this T and change it to an R. What does it say now? Dog R, big ham. Doesn't make a whole lot of sense. But, I mean, you still get some sort of English. Now let's do an insertion mutation. And keep our three-letter reading frame. Now it says, dog, pat, ebi, ga, It really messed up my sentence. Similarly, in real life, DNA mutations that do that insert or delete, totally mess up the reading frame. They're called actually frame shift mutations because they do that. For example, putting in a G, an extra G, in that same string of nucleotides, adding a G in between the T and the A, instead of just changing one to the other, we're still going to read them 3 by 3. What are our 3 amino acids going to be now? Again, you're going to have to do this on homework and on test, so it's worth practicing right now. What'd you get? Come on, I did one step for you. Tell me besides Riley. I know Riley's got it. Benny, what do you got?
For the first one,
Hmm?
I got
Everybody agree?
Yep.
Second one?
alanine
Cool.
and then glutamine.
Are any of those the same as they were? It changed all of them. And in fact, any mutation like this is most likely going to change every amino acid after it. And very likely totally ruin the protein. Because all it takes really for a frame shift mutation is exactly what Landon was asking about. Hey, isn't it pretty likely that sticking an extra base in there is going to screw up the frame to where we don't hit the stop codon at the right time and get an infinite string of amino acids that's just a glob that's non-functional? Or, equally likely, hit a stop codon early, cut the protein off before it's fully formed. That's not good either. So, That's the idea. Any mutation, three things can. Number one, nothing. And believe it or not, that is by far the most common effect of a mutation in DNA. And that's because, again, believe it or not, 97% of your DNA doesn't code for protein. You would be amazed at how much sort of filler DNA there is and how much DNA there is in between genes. Also, remember that RNA transcription only happens on one of the two DNA strands. So if you mess up the other one, it's not going to do anything. So no effect is by far the most common. Helpful effects can happen, are extremely rare, but turn out to be kind of the whole basis of evolution. Right? You're in a very real sense a collection of the mutations that worked for your ancestors. Point at anything you got, any of your best features, nose, eyes, muscles, started as a mutation, right? Worked really well. So your ancestors did better than their neighbors, and so you've got eyes. Pretty good one. Not as good as fish eyes. Fish see better than you. Yeah. Well, your eye is full of water. So it's much easier to see underwater with an eye full of water than to have to deal with the refraction. Chris?
Can birds actually see 360 degrees like vision?
360 degrees.
Like apples?
I mean, they can turn their heads. Yeah, I mean, they can cover that by turning their heads, but their eyes don't just I don't know. Yeah. All right, so no effect, most common. Harmful effects, probably next most common. Helpful effects, rare but essential to evolution. That's the idea. All right, coming at you now. Let's look at some mutations. This is like yesterday's homework, but now we start messing with things. Now you got to start seeing what the changes do. So again, very similar, except we're always starting with DNA now. Okay, the top line, you're always going to be given the DNA. You got to take it through mRNA. You don't have to do tRNA this time because we don't need it, right? You put the mRNA directly in the wheel, we're good. So you do that, you transcribe and translate it. You're starting at the top with the unmutated DNA, right? The original DNA. So that's normal. We're going to call that normal. Then they throw a bunch of mutations into that sequence, and you got to kind of make calls about what that did and what we're going to call it and stuff like that. Okay, that's kind of the whole thing. Yeah, go ahead and get started so you know what you're doing. At least do the original while we're here. And I would like that done for homework. Let's make that one due on Friday. I'll give you 2 days for that one because I am going to give you another assignment tomorrow. I have pushed the test. We're not going to make a test by Friday. Test is Tuesday. Okay, that's a fairly firm date. Tuesday is your chapter 12 and 13 test. Any questions?
Are you gonna do anything like you did last time where there's gonna be like something from like chapter 14? Some weird shit
Maybe,
that I-
maybe. Yeah, I might. Certainly, I really like to hammer back on meiosis and how variation happens. That's a good thing to look for. It's kind of gonna be a running theme.